everybody. So, hopefully you guys have had a chance to look at all the elastic and inelastic problems that we did, and if you had any troubles with those, I put all the solutions on our website. If you have any questions, just send it to the Discord or just send me an email if you'd like. Go from there. Now, today, this is fun. Okay, this is like a Mr. Stone lesson. This is gonna be fun. We're gonna divert away from just the simple Newtonian kinematics and dynamics here. We're gonna do some modern physics. We're gonna talk about some stuff that's actually happening now. Some neutrino physics. Looking at some real modern physics problems. Okay, so we're gonna talk about beta decay, which hopefully you guys have I think I talked about it in class a little bit, where electrons come from and that sort of stuff, and weak interactions and all that sort of weird things. So let's think about some of the stuff that we've done here. So let's start with what we know so far about the universe, what makes up all the stuff in the universe. So far, according to grade 10, even grade 11 chemistry, probably even grade 12 chemistry, there's only three things that make up the universe. We got protons, neutrons, and electrons. You stick them together, you get an atom. You do things, you do chemistry with those atoms, right? We have this little tiny grain of sand here in the middle of the thing, right? If this whole room was an atom, there'd be this tiny little speck of sand that contains all the mass, and we call it the nucleus, and it contains all the protons and neutrons, the nucleons, we can call it. And around them is this haze of electrons buzzing around in these shells, these S and P and all d orbitals and all sort of weird stuff like that, right? Now, that's what you guys have learned. The modern view of the universe is a little bit more complicated. It's not much. It's just a little bit deeper into those nucleons, and there's a few extra things. But we call this the standard model of subatomic particle physics. It's called particle physics. The idea of all this idea of what is the universe made of, and how do all those things that make it up interact with each other. And currently there's 16 and then one extra, so 17 subatomic particles. What are they? How did they get discovered? So this is the picture that we see now of our modern view of the universe. So we have, what do we have here? Where's my pen? Where'd I do my little? Where'd it go? Oh, where's my funky little? There it is. Found it. A little little computer pen. Kind of fun to play with. Okay, so here we have what we call the quarks. So this group here, you can't even see the cursor. Yeah, there. This group, this is the quarks, right? This is what makes up all the mass in the universe. What we interpret as mass, okay? So we got up, down, which makes up most of our protons and neutrons. Charm, strange, bottom, and top. Okay, and it shows here they have sort of effective masses in this really strange unit, mega electron volts per d squared, which we'll talk about this in Unit 5. Okay, so this is the mass of the universe. Okay, and then we have much smaller things. We have an electron. We all know what electrons are. Then we have a slightly different flavor of electron, fermionic flavor. These are called the leptons. All this whole left-hand side here, maybe we can break this up. We got on this side, these are the fermions. And these over on this side are the bosons. And the difference is that fermions can't exist in the same quantum state. They have you can see here, they all have spin halves. These all have half spins. Every single one of these, they all have half spins, which means that they obey what we call Fermi statistics. They can't exist in the quantum state. Like for example, when you looked at your in grade 11 chemistry, remember we had to Pauli's exclusion principle. You had to put electrons up and down. So in that quantum state, there can only exist an electron up and an electron down. Bosons are different because they can coexist in the same sort of quantum state. So photons don't care about the fact they're together, they all can have the same quantum state. Fun thing, we can actually take matter, and if you get it cold enough, they can sort of pair up with each other. They can end up behaving like bosons. You can take helium, and the helium atoms can get into a state when they're cold enough where they have integer spin. Then the whole helium mass can all end up with the exact same quantum state. We call this a Bose-Einstein condensate. This is where you get superfluid helium, where every single atom, all 10 to the 24 atoms of helium in this container of helium, all are in the exact same quantum state, and they behave like what we call a superfluid. They have superconductivity. Electrons can pass through them with no resistance. They have no viscosity. They can come out of the thing. It's very strange. Only happens at like I think for helium, it happens at negative 2.7 Kelvin, I think. It's very, very, very cold. So liquid helium. Look it up. Fun stuff. Okay. So there's the fermions on one side, bosons on the other side. Okay. So we have all the matter, our nucleons, mostly up and down. That makes our protons and neutrons. Then we have our electrons that we're used to, extra flavors. Then we've got these funky things called neutrinos that are completely strange. Notice here, we don't have a mass, we have a less than. We don't know what the masses are of neutrinos. We're still working on that. That's one of the undiscovered things. We have an upper bound here for the mass, right? Sorry, is that a... So it has to be less than. So yeah, it's an upper bound of what our masses could be. Then we have over here, we have the bosons. These are the force carriers. We call them force carriers because they are able to pass on our forces, our 4 elementary forces. Well, gravitons aren't even in here because we have gluons that obey that pass on the strong nuclear force, photons that pass on the electromagnetic force, and these two, the Z and the W bosons. The Z, you can call this a Z naught, Z0, and this is a W plus or minus. These are the weak interaction force carriers, and there's a neutral one and a charged one. And then we got this really funky. This is very new. This is as of 7, when we started to use what we called the Large Hadron Collider. I think it's 2007. Maybe it's not. Get rid of that. I don't remember exact date here. But we just discovered a new particle called the Higgs boson that transmits what we call the Higgs field. And we think this is where mass comes from. This is where inertia comes from. That last fundamental problem of physics of Newton's first law, everything that has mass has inertia. Why? And we think it has to do with the Higgs boson. Okay, so this is our view. This is the particle physics view of the universe as it is. These are the 17 things that make up everything. Okay, this is our view of how the universe is made. We have quarks, we have leptons, that all together we call fermions, and then we have bosons that pass on interactions. So these are the types of matter, right? So you have matter in the form of quarks, electrons, and neutrinos. Then we have force carriers, which we call bosons. Right? And don't worry about the fact that there's vector and scalar. What a gauge boson. This is one of the favorite words for modern particle physicists. Gauge fields. You look at the interaction of gauge fields in quantum chromodynamics. Blah, 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 all that sort of fun stuff. Okay, so this is the universe. Okay, you are looking at the universe as we know it now. Remember that anytime we do physics, it's always a approximate view of the universe. Newton was not wrong. He was right to a certain accuracy, certain precision. Then we start looking closer and we find little mistakes and we refine the picture. It's not saying that anything was wrong before this. Your view from grade 10 of, an atom is, let's say, sodium, 11p, 12n, then we do this 4 Rutherford diagram, right? 1, 7, 8, 10. and 11. That view of a sodium ion atom, sorry, is not wrong. It's just an approximation of the truth. It's not saying that that is false. It is an approximation. And we learned all about those other things like orbitals and that sort of stuff, and go on from there. But this is our most accurate. It might be wrong. It might be like there might be something fundamentally wrong with this, and we have to refine it. But this is, as of 2020, this is the most accurate view of what the universe is made out of. Okay. So let's talk about beta decay. So beta decay ends up being how we. It's one of the ways in which things fall apart. Okay, one of the ways in which stuff decays. It's a nuclear process in which nucleons, or the nucleus of atoms, fall apart and give off stuff. In this case, electrons. So the first time that we've talked about this is from a neutron. So neutrons are very, very slightly unstable. Neutrons can't actually exist for infinite time scale. Protons we think have an infinite time scale, but we have no idea. We don't know yet. As of now, protons have a infinite time scale. However, neutrons we know are slightly unstable and are able to fall apart. They decay into a new proton, so the neutron becomes a proton, and while it does that, it gives off an electron. This is a process of beta decay, and this is actually beta minus decay because it gives off a negative electron, right? There's actually beta positive decay, which is when we give off a positron, which is the antiparticle of an electron. So here, this is actually shows us a an event in which a neutrino, about that later, comes along. So comes along here and it hits a neutron. We can't see a neutron in this. This is called a cloud chamber picture. Cloud chamber is a bunch of suspended alcohol, and when charged particles whiz through it at high speed, it condenses on them. Can't actually see them here. But at this point, a neutrino came along, hit a neutron, and it broke up into a proton, and then a bunch of extra stuff here. So this is the first time that we actually saw, this is a special type of beta decay. They gave off a bunch of mesons. Mesons are two quarks together, and slightly different, but let's not worry about that for now. This is just showing a proton decaying from a neutron that you can't actually see. It's invisible stuff. Okay? So let's see what happens. So this was the view of, this is what we would see from a Newtonian viewpoint. Okay, so we have our this is our neutron here, and it breaks up into a proton and an electron. And notice because the proton's mass is much higher than the electron's mass by a factor of 10 to the, what is it, 10 to the 31 minus 20, 10 to the 4 times bigger. It's 10,000 times heavier, 2,000 times. So that means that the order of 10 to the 4, which means that the velocities, because of conservation of momentum, the velocities are also going to be in that same order, 10 to the 4 times different. This electron's going to whiz away super fast, and the proton's just going to putter off, right? But the important thing is that this whole system is one-dimensional. They're collinear with each other. This is what we would expect to happen when a proton and a neutron decay from a neutron. Right? Proton and neutron are made when that neutron decays. However, what was actually seen, was actually observed, that the electron whizzes away. So, because we know that conservation of momentum has to be true, there has to be a invisible sort of particle that we can't. At this point, we're talking about 1930s here. This is Wolfgang Pauli. This has to be this invisible dude who very light and interacts weakly interacting. So it doesn't interact with charge. It doesn't interact gravitationally, we don't think, and it has to be produced there. Okay, so this is to satisfy this equation. Right? If that was broken, then that's something fundamentally wrong with our understanding of physics. We want to keep that going, so we have to have this thing. And To conserve this momentum, a guy called Wolfgang Pauli, again with the Pauli exclusion principle, same guy, came along and he theorized that there has to be this third thing showing up here. Third guy showing up is a weakly interacting light particle that has to be present in the collision. He called it a neutrino, okay, which is Italian for small neutral particle, a neutrino. It's neutral and it's very small. Small is in very, very small mass. Okay, and it took until 1956. So this was theorized in the 30s. It took for 1956 to actually discover where if this particle truly existed. And that's because weak interactions are very, very difficult to see because they don't interact with charge. We can't manipulate them with magnetic fields or electric fields. Right? They don't. They hardly interact gravitationally, so we can't sort of weigh them. Right? So this has to. So we have to produce this third thing that's very, very hard to find. Now, what's interesting here also is this bar on top. This bar on top means that when I'm doing this, that bar on top to exist there, that's an anti-neutrino. I have a regular neutron showing up here, proton showing up here, and an electron. This is all regular matter, but I'm starting out with one piece of normal matter. Two pieces of normal matter are made out of it. So to balance that, what we call to conserve the lepton number, we have to have this anti-particle show up. Okay, so this is a electron neutrino. Remember that's nu. It's the Greek letter mu, and it's an electron. The flavor of neutrino is an electron, and it's an anti. This is an anti-electron neutrino that shows up. Okay? That's because something called lepton number has to be conserved. Don't worry too much about that. Okay, so this is the modern view of beta minus decay. So this is our first example here of a weak interaction, and it's very hard to see, and it doesn't happen too often because it's what we call a weak interaction. So it's moderated by the weak nuclear force. Remember, if we go back, we have our fundamental forces are electromagnetism, strong nuclear force, so that's the force that holds the nucleus together, and the weak nuclear force. And then there's gravity. We don't really understand yet. Gravity does not fit into our standard model. That's like the holy grail of particle physics, is where is gravity in the standard model? We're not there yet. One day, one of you might discover why. Okay, but keep going. So this one that we're talking about here is called the weak nuclear force. That's moderated by W plus or W minus or Z naught bosons. Okay, and in our modern view, this is what happens. This is what we call a Feynman diagram. There's a guy called Richard Feynman, probably, in my humble opinion, the most brilliant physicist of the 20th century. Last century. Einstein's up there, but I think the fundamental work that Feynman did in understanding particle physics and just this fundamental view of the universe, brilliant man. Richard P. Feynman from Long Island, New York. He has some marvelous books. He had a lecture series when he worked at Caltech. He was a lecturer at Caltech. Did a course, and there's a course of books, Feynman lectures. There's 3 books. I have a copy of them. I think Mr. Francis has a copy of them. They are the greatest physics textbooks. They're incredibly difficult to get through, but they are the best physics textbooks to give you an understanding of modern physics as it stands here. So what happens? This is a Feynman diagram. This shows a neutron here. This is where we start. Okay, we have a neutron, and it's going along, and it's made up of, neutrons are made up of quarks. three quarks: up, down, and a down quark. Those are the quarks that make up a neutron. Okay. But we have these up, down, down quarks. Okay, and this one down quark comes along, and at this moment it breaks down. It falls apart into an up quark. So this neutron, this up, down, down, that made a neutron. One of the down quarks came along, and at this point decayed into an up quark. It changed its what we call flavor. It changed its quark flavor from a down to an up quark. And now we have an up, up, and a down quark, which makes a proton. Okay? So we went from a neutron to a proton. Okay? So then what happened also, for that to happen, it has to give off a boson, right? Because there's some forces acted on this to change the flavor. It gave off this weak boson, this weak W minus boson. Okay? So that's where that negative charge went to, because this went from a neutral neutron to a positive. Right? To conserve charge, we have to have a neutral, a negative thing being made. So that's a negative W boson. It exists as a virtual particle very quickly, and then it also falls apart. We have a decay here, and this thing also decays into an electron that heads off this way. So there's our negative charge and our anti-neutrino, anti-electron neutrino. Right? So first we have our neutron, and then we have our proton. Decayed that, so that up down quark decayed into a boson, and then the boson itself decays into two actual particles, which is an electron, a antineutrino. Now, these arrows represent time. So time is going up. This x-axis doesn't really exist. It's sort of like a space axis. It sort of gives us a sense of where this is happening. Notice that this arrow is down, which means antiparticles from a Feynman diagram point of view are traveling backwards in time. Really weird, and we're not going to think about that. Okay, we're just going to leave that. But the important point here is that this weak interaction, what it does is it changes flavors of quark, and it follows the rules of what we call quantum chromodynamics, QCD, which is a field of physics which we really don't understand. This is one of the frontiers of physics, quantum chromodynamics. Okay, QCD. And so this is the modern viewpoint of beta decay. Right? So this is a neutron decaying into a proton, giving off two extra things, one being an antineutrino, and the other one being an electron. Okay? So the question becomes, how do we detect these neutrinos? Now, this is possible because this beta decay process happens, can happen in reverse as well. So for example, here we can have a neutrino coming along, electron neutrino, this comes along, and it smacks into a neutron. Oops, what? Okay. Smacks into a neutron. Okay, and that creates a new proton and an electron. Okay, and this happens because we can see this occurring here. This is what happens in these detectors. We have a deuteron, which is just a hydrogen, regular old hydrogen nucleus, but there's an extra neutron. So D is a thing, instead of hydrogen is 1, 0. Deuterons are 1, 1. So they have 1, 1. Sorry, hydrogen has a mass of 1. Deuterons have a mass of 2, which means they have an extra neutron. If you put this into, let's say, take 2 deuterons and add an oxygen to it, you can end up with what we call heavy water. It's regular old water, but it has twice the mass. Well, the hydrogens have twice the mass. So each water molecule weighs 18 atomic mass units, as opposed to 20, as opposed to 18. Right? So this electron comes, the neutrino comes along, and Again, this is one of these Feynman diagrams. Takes one of the down quarks and transmogrifies it into an up quark, changing it from a neutron to a proton. Okay, so we end up having these two protons being created. Well, the one original one and the other one here. And we have an electron also showing up. Okay, so the input was a neutron and a neutrino, and we end up with a proton and an electron come off. Okay, so we can actually see this. You take heavy water, you let it sit for long enough, you put a whole bunch of detectors around it, and then you look to see electrons being formed. Okay, and this happens in our neutrino detectors, like the Sudbury neutrino detector, or the one in Japan, or IceCube down in Antarctica. This is what we want to see. Okay, another way. So that last one, sorry, this is mediated by a charged W minus boson, or it can also be mediated by a neutral boson, which is when one of the neutrinos comes along and it just changes the flavor of this quark. It doesn't change it doesn't change the flavor. It can change the color, it can change the types of these guys. This is very difficult to see, right? We can't. It's also another possible way of happening, but we can't actually see this in a detector, right? This is not a way. This is one of the other ways that happens. It's just not very useful for us from a physical point of view of detecting neutrinos. So here's the Sudbury Neutrino Observatory. So you can see in this picture here, this big glass ball is an enormous glass ball, and it's filled with that heavy water. Filled with, oopsies. It's filled with a whole bunch of it. And then on the outside is all these detectors. These are called scintillators. They're little, they're electron catchers, basically. Sorry, no, not electron catchers. They're light photomultipliers. They're allowed to detect incredibly weak light sources. They multiply the regular light that comes in, and then we turn it up into a much higher voltage, and we're able to detect light. So this is it with most of its detectors off. This is all of its detectors in here. This is the old Sudbury nickel mine. The big cavern in the old Sudbury nickel mine that they converted into the Sudbury Neutrino Observatory. So let this sit, heavy water, and they detect those electrons that come off. But then you got to think to yourself, okay, so electrons are coming off. Why do we see light? Why is it important that these are photomultipliers that are detecting them? Where's the light coming from if these electrons are there? And that comes from this idea of what we call Cherenkov radiation. This is awesome. We always say that nothing can travel faster than light, but what happens if things do travel faster than light in their medium? So here again, this is our deuteron here, our heavy water deuteron. A neutrino comes along, smacks into the neutron, creates two protons, and remember this is an electron. Now this electron has an enormous amount of energy and is traveling very, very fast. And it travels faster than it's traveling faster than it should in the medium. Okay, so when it's a tricky idea here. So this is giving off light because we know that light has a speed of c, which is 8.0 10 to the 8 meters per second. Right now, remember, we learned in optics that v is equal to the speed of light in the medium divided by n. So remember, this is the index of refraction, how dense optically a material is. So heavy water is about the same as regular water, about 1.3, so 4/3. So this is going to multiply our c by 3/4. It's going to be 3/4 of the speed of light. So if this electron is traveling faster than that, it produces what we call Cherenkov light. It produces this cone of blue light. All right? And it allows us to see that. So this electron whizzing at some ridiculous speed, because it's traveling in this water that has a speed of light, of the speed of the medium, speed of light in that medium lower than the speed of light, it produces Cherenkov radiation. You may not believe me, but check this out. This is a nuclear reactor. It's a research reactor, but it's still a nuclear reactor. It's a whole bunch of uranium in there, and they're going to turn it on. They're going to start the fission process, and the fission process produces all kinds of radiation, tons and tons of radiation, an immense flux of radiation. Let's see what happens when they turn it on. And this is immersed in water. Okay, watch what happens. Oh, where's all that blue light coming from? That blue light coming from? That's Cherenkov light. That's all the decay materials that are coming off of uh, the uranium fuel rods in there, just glowing bright blue. We're totally safe here because that water is actually stopping all those radioactive particles from getting to us. If you were standing there in front of, I don't know if that's glass or that's a camera, or it is a camera, I guess, because we can see it. But I don't know if you can actually observe this real time from a glass window or something, but it wouldn't matter because that the water is stopping all the radiation. You can see that blue glow of all that Cherenkov light coming off of there. Exact same thing happens in the Sudbury Neutrino Observatory, but it's much weaker. Okay, and it only happens like once every 2 days or something. Right, so this is Cherenkov light. This is a much more luminous version of Cherenkov light. The same thing happens in the Submarine Neutrino Detector. Also happens at SNO, which is the IceCube. Sorry, SNO is the Sudbury Neutrino Observatory. There's another one called IceCube in Antarctica. I'm gonna put a link in the link in the description for this video of a bunch of different videos describing how this is done. One of them is called IceCube, how they built IceCube, why neutrinos are cool. Just check out all the videos, okay, in there. So that's my little discussion. Hopefully I didn't confuse you or lose all of you on all this nonsense about modern subatomic particle physics. But all I want you to do, excuse me, talking lots. So what I want you to do is I'm going to check on the website. There's a link to a PDF of some reading from a textbook about beta decay. So go to the beta decay part, read the beta decay thing, and then there's a bunch of conceptual problems. Okay, I want you to do those problems. I'll post the answers again, post the answer for everything up there as well. Okay, so if this confused you, go back. Remember, you can always stop these videos, go back, and if you get confused again, you know, just send me a message on the Discord, send me an email, whatever you want. I love this though here. History of physics. Okay, so Aristotle said a bunch of stuff was wrong. Galileo and Newton fixed them up. Then Einstein broke everything. Now we figured out basically everything, except for small stuff, big stuff, hot stuff, cold stuff, fast stuff, heavy stuff, dark stuff, turbulence, and the concept of time. Really, we don't know anything. We have an approximate understanding of the universe. There's so many questions. That's why physics is awesome. Please continue your learning of physics after this course because there's no end to it. The best part about physics is there's no end. All right. So I hope you're all well and stay safe out there. Remember the rules. Stay safe. Stay home. Do physics. All right. Take care.